Welcome, Math 3 students, grade 9, to your last chapter, Science for Math 3, about Sun, Earth, Moon System, and Space Technology. This is chapter 8. You're about to finish your book. Topic 8.1 Gravitational Forces. Question: does the moon rise and set at the same time every day? Why? Now, let's talk about gravitational forces. Besides the 8 planets, there are many other objects that revolve around the sun. They are the asteroids, meteoroids, and comets. Beyond Neptune, there is a ring of ice. There is a ring of icy bodies known as the Kuiper belt that revolve around the sun too. In this belt, there are 3 recognized dwarf planets which are known as Pluto, Haumea, and Makemake. These objects revolve around the sun due to the gravitational forces acting between them. Newton's law of gravitational or Newton's law of universal gravitation states that the attractive force between two objects is directly proportional to their masses and inversely proportional to the square of the distance between them. I want you to read this formula. F equals G times M sub 1 times M sub 2 divided by R squared, where F equals gravitational force between the two objects, and G equals gravitational constant, which is 6.67 times 10 to the negative power 11 m cubed per kilogram per second. Like m sub 1 equals mass of the first object, and m sub 2 equals mass of the second object. R equals distance between the objects. Here's the amazing facts. There are attractive forces between us and the things around us. However, these forces are very small for us to notice as the objects have very little masses. The strength of the gravitational force attracting the two objects together goes up as their masses increase and decreases as their distance increases. This force acts across even the huge distances between the sun and planets. The masses of the sun and a planet create a force pulling the planet's orbit into a circle. This law applies to any objects, not just the planets and the sun. Example: there are 2 stars. The first star has a mass of 2 times 10 to the 15th power kilogram, and the second star has a mass of 4.5 times 10 to the 16th kilogram. If the stars are 2,000 kilometers away, what is the gravitational force felt by the first star? Solution: F equals G times M sub 1 times M sub 2 divided by R squared. So equals 6.67 times 10 to the negative 11 times 2 times 10 to the power of 15 times 4.5 times 10 to the 16 divided by the quantity of 2 times 10 to the 6 squared, all squared. And so 1.5 times 10 to the 9 Newton. Wow. So we have the common mistakes. Number one, the gravitational force is inversely proportional to just the distance. This is r. Second, the distance, or r, is the distance between the surfaces of the objects. But the truth is, number one, the gravitational force is inversely proportional to r squared, not just to r. And second, the distance r is the distance between the centers of the objects. Okay? Now let's watch this Newton's law of universal gravitation.
Professor Dave here. I want to tell you about Newton's law of universal gravitation. He knows a lot about the science stuff. Professor Dave explains. We learned about Newton's laws of motion, but there's one more law of his to discuss, and it's a big one. It's Newton's law of universal gravitation. In possibly one of the greatest strokes of genius in the history of mankind, Newton looked at the motion of the planets in their nearly circular orbits around the Sun and understood that the centripetal force causing this motion was precisely the same force that causes objects to fall down towards Earth, which we call the gravitational force. In this way, he proposed that the planets are in a kind of free fall towards the Sun, just the same way that the apple that mythically hit him on the head to produce this insight was in free fall towards the Earth. The objects differ greatly in size, but the concept is the same. Newton corroborated this notion with a thought experiment. When a cannon fires a cannonball, the ball eventually hits the ground. If another cannonball is fired with greater force, it will go a little further before hitting the ground. If a cannonball could be fired with an incredibly immense force, it could produce a speed so great that the ball would never hit the ground, since it would fall at the same rate that Earth's curvature is produced. It would thus always be falling towards the Earth, but never hitting it. Such an object would be said to be in orbit around the Earth. Of course, no cannon can do this, but we have finally achieved this feat with all of our satellites and space stations, which are brought up to orbit on rockets. These are very far from Earth's surface, and they are moving with such great speed that they, along with anyone on board, are always falling towards the Earth, but never hitting it, in a free fall, just like Newton's apple. This means they orbit around the Earth indefinitely at a fixed speed and radius. The same can be said for all the planets around the Sun. This gravitational force can describe the motion of every object in space, and it is the case that every object that contains mass will exert gravity on every other massive object. Of course, to feel the effects of gravity, we must be near an enormous object, like a planet. But it is completely accurate to say that gravitational force is exerted by your car, your refrigerator, even you yourself. It is just that this force is completely negligible compared to the gravitational force exerted by the Earth. Newton developed an equation to quantify the magnitude of the gravitational force between two objects, and it looks like this, where F is equal to the constant of universal gravitation, g, times the mass of the first object times the mass of the second object divided by the distance between them squared. This constant, like any other constant, simply exists so that a natural phenomenon like gravity can be expressed in our own arbitrary man-made units, and it is equal to 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. These are the units that will cancel out the units on the masses and radius so as to give a value for force in newtons. This value was not known to Newton at the time, but was determined experimentally about 100 years later by Henry Cavendish. When discussing the radius between two objects, we will take the distance between their centers rather than their surfaces, as Newton showed that the gravitational force exerted by an object depends only on its mass and not on its volume, meaning that when discussing gravity, we can treat everything as a point-like mass. He had to invent the calculus to do so, much to the dismay of math students everywhere. When examining a system like the Earth and the Moon, we must understand that both of these objects exert gravitational force on the other, and that these forces are equal in magnitude, meaning that both of these bodies rotate around their combined center of mass. But don't forget that F equals ma, so equal forces will not produce equal accelerations if the masses are different. As it happens, the Earth is much, much more massive than the Moon, so the mutual gravitational force is able to accelerate the Moon more than the Earth, and the center of mass for the system lies within the Earth itself, which is why we simply observe the Moon going around the Earth. The same can be said for Newton's falling apple. The apple accelerates towards the Earth, and the Earth accelerates towards the apple. But the Earth is more massive than the apple by an inconceivable factor, so the acceleration of the Earth is not even measurable, whereas we can visually confirm the acceleration of the apple. Furthermore, we want to understand that an apple will fall to the Earth with the same acceleration as a bowling ball or any other massive object, if we disregard wind resistance. Although counterintuitive to some, we can rationalize this if we understand that while the force of gravity is able to impart greater acceleration on a more massive object, the more massive object also has greater inertia, or resistance to being accelerated. So the end result is that all objects accelerate towards Earth in the same way, at 9.8 meters per second squared. This fact is easy to derive if we do some algebraic manipulation. We know that a falling object exhibits behavior according to Newton's second law, F equals ma, where the force that generates the falling is equal to the mass of the object times its acceleration. But this force is the gravitational force, so we can also model the falling behavior with g m1 m2 over r squared, where m1 is the mass of the object and m2 is the mass of the Earth. If we set these equal to each other, the mass of the object is found on both sides and will cancel out, so we can see that the acceleration due to gravity is equal to the gravitational constant times the mass of the Earth divided by the radius squared. This means that the mass of an object does not affect the rate of freefall.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Newton's work on gravity was revolutionary. It correlated an incredible amount of data, from terrestrial motion to celestial motion, which is all any good theory can hope to do. But he could not explain how objects can exert the gravitational force on one another from a distance. Later, scientists solved this problem by labeling gravity as a field force, stating that matter generates gravitational fields in space. This was a bit more satisfactory, but it wasn't until Einstein's general theory of relativity that we arrived at a more sophisticated understanding of gravity, which has helped us learn about the structure of space itself, as well as how planets and stars and galaxies form. We are still trying to fully understand gravity today, but the continuation of this discussion will have to wait until the modern physics course. So for now, let's check comprehension.
Checking comprehension. What is the magnitude of the gravitational force between a 75 kilogram person and a 90 kilogram person and 5 meters apart?
Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Thank you, Professor Dave. My students have learned a lot from you. Now, you don't have the workbook. Let's go directly to the conclusion. The conclusions are in the solar system, the sun is the center. The planets and celestial bodies, dwarf planets, asteroids, comets, and others, such as the objects within the Kuiper belt, orbit around the sun due to the gravitational forces acting between them. Gravity is the attraction force between two objects that is directly proportional to the product of both masses and inversely proportional to the square of the distance between them, with the equation F equals G times M, or the first mass object, and M, or times M, sub 2, or the second object, divided by r squared, where F represents the gravitational force between the two masses and G represents the universal gravitational constant. When M1, or the first object, or first mass, represents the mass of the first object, and M2 represents the mass of the second object, and R represents the distance between the two objects. I want you to turn your book to page 151 and check how much you understand this subtopic by doing or answering Test Yourself 8.1. Okay? And come to me. I will check your book to see if you're a good student. All right, and I will give you bonus points and then post that in our line group. All right? Well, see you next time. Bye bye.